and co-founder of Turntide Technologies. So I'm going to just talk about SAE for just a couple minutes and then turn it over to Alvin Chin, my counterpart at IEEE VTS. And then we'll turn it over to Piyush Desai to go through his presentation. First, I think everybody besides the panelists are on mute and blocked for video. If there are any questions along the way, please use the chat feature. We'll also use that for questions at the end. The presentation is going to be about 45 minutes, and then we'll have 15 minutes or so to address the questions, probably in the order that they come in. So if you can use that, that would be appreciated. A little bit on SAE, if you're not a member of that or not familiar with it. We are part of SAE International, so we're for the Chicago section for everything mobility. So it's beyond what SAE used to stand for, is Society of Automotive Engineers, and focusing more on just overall mobility. So it includes aerospace, commercial vehicles, and passenger vehicles. Chicago is one of the largest sections and probably one of the more active ones in SAE International. And with our membership, we have about 200 various companies just in this area represented. So overall, we have about 1,000 members. 850 of those approximately are professional members, and then about 150 university student members for the schools listed there. Most recently with Bradley, which is closer to the mid-Illinois, central Illinois section, but they've decided to participate in the Chicago section for at least the foreseeable future. I won't go through this whole chart, but this gives you an idea of the number of officers involved in the section, a wide variety of backgrounds, expertise, stages of the career, everywhere from retirees to a couple that are still students, and then early in their careers. So it's a nice mix. Last couple of years, we've done a good job of recruiting and getting members involved at the member or at the officer and the board activities. We have monthly board meetings throughout the year. Second Tuesday of every month in the evening, we do just a phone call, webinar type thing. So if you want more information on that, you can reach out to me or any of the officers here if you recognize any of the names. And then to keep up to date with SAE Chicago, we do have a new website that we're starting to promote. Listed there is chicagosae.org. And then we're also on LinkedIn and most recently Twitter, thanks to the help of one of our younger student members. So we're advertising and promoting our events through that. Upcoming events, we have one coming up in less than 2 weeks on Tuesday, February 2nd, that we're just starting to promote. It's with a presentation from Caterpillar and their mining operations president. Going to talk about their autonomous mining programs. So I'm looking forward to that presentation. On Thursday, the 18th, we are having a virtual student event where all the university programs involved with college design series programs, being the Formula, SAE, Baja, and then the high mileage and hybrid vehicles. They're going to make presentations, and then we're divvying up the annual funds that we donate to the universities to support in support of those programs. And then late in March, this is more of a save the date. We got a presentation from Clear Flame Engine Technologies on their development of a very clean diesel program without having to use DPF type things. So a lot of activities. It's been a challenging year, as I'm sure Alvin will attest to, without being able to meet face to face. and doing events like this where we're having to do a virtual, but we're working through it just like everybody else is, and we got some good events coming up. So with that, I will let Alvin speak to the next couple of slides.
All right, thank you, Tim. So my name is Alvin Chin, and I am the chair of the Chicago section for IEEE Vehicle Technology Society. And you can see there's our website, IEEEchicago.org/VT. The VTS Society is vtsociety.org. My day job is I work for BMW Technology Corporation. Our vice chair is Kevin Studenberg from Argonne National Laboratory, and IEEE Young Professionals BTS student chair is Juro Chen from IIT. So we have done lots of meetings together with SAE Chicago. So we really thank SAE Chicago. We have a great partnership together. It started about more than 2 years ago. We had, a lot of meetups, within BMW and as well with other locations. And of course, now we're doing this, continuing to do this collaboration virtually online now. So we really thank SAE Chicago for their support in our events. And also we are also helping with them because we all have common topics. If you want to become a VTS member, you can go to vtsociety.org/engage/membership. And like SAE Chicago, we also on Facebook, LinkedIn, and Twitter. And we just launched we have a Vimeo channel. So if you want to see our previous VTS Chicago seminars and webinars, you can go to the Vimeo link there. Next slide.
Did that not come up, Alvin? I'm sorry.
Yeah, somebody just said that the screen was not showing, so we might need to reshare.
No, I just see only. Okay, it's coming up. Yeah, so the Vehicle Technology Society, we have a conference that happens twice a year. The one we just finished was actually last year in November. It was a virtual conference, obviously, from what's been happening. So that's the link there. We're actually planning to do a kind of a conference summary of what happened during that conference sometime in February. So please look out for that. And then for this year, there's going to be a spring and fall technology conference. The first one is going to be in Helsinki.
Hey, Alvin, sorry to interrupt. The screen went black.
Everything is okay there. And if you're interested, oh, okay, sorry.
Yeah, we lost your screen, Alvin. Sorry about that.
No, it's still me. Yeah.
Okay.
I don't know what's going on with that. I apologize. It's
our
last slide anyway.
So.
Little technology. Is that visible? Every time I go to presentation mode, it blanks out.
Correct.
Okay.
Need to invite the Society of IT Professionals to these in the future. So.
All right, Alvin, I think is your last slide up there now? Are you able to see that?
I just see only the beginning slide, and it's not in presenter mode.
It's not in presenter mode, but we see the IEEE vehicular slides. So.
Okay.
The standard PowerPoint.
Yeah.
All right. Did you?
Oh, you do see? Okay, I don't see. But,
yeah.
I don't. But anyway, yeah. So.
Yeah. All right. Last chance. That's it.
Yeah, I see your slide number 6, not in presentation mode, but at least I can read it.
So, as soon as I hit presentation mode, it goes blank.
Yeah,
so.
Yeah.
All right. So was that it, Alvin? Were you?
Okay.
Did you cover all these?
Well, anyway, like I said, yeah. Yeah, that's pretty much about it. So that's the links if you are interested in wanting to know more about the conferences. The VTC 2021 spring is open, so you can start to have a look to see if you want to participate in it. So again, thank you very much for SAE Chicago for inviting us.
All right, thanks, Alvin. Again, this is Tim Hicks, the SAE Chicago chair. And without further ado, hopefully we have a better luck with the presentation from Dr. Desai. But without further ado, introduce the Turntide VP and co-founder, Dr. Piyush Desai. So.
Thank you, everyone, and nice to meet you via Zoom. It's a great pleasure to be here and sharing some of the learnings and information and experience here with my colleagues, working professionals, and passionate engineers. I really appreciate the opportunity to share this presentation with you. And I hope you would enjoy it. So I'll share my screen. Do you see?
Yes, sir.
Looks
Presentation?
great.
Yeah. So yeah, I'm Piyush Desai, and I'm VP of Motor Design and a co-founder at Turntide Technologies. I co-founded this in 2013 with some Silicon Valley serial entrepreneurs to commercialize patented high rotor pole switch reluctance motor technology that I developed during my PhD at Illinois Institute of Technology from 2002 to 2009. So it's a personal journey about going from concept to a PhD and commercializing it. Turntide is a company in Silicon Valley. We have about 150 full-time employees. It has offices or labs in Seattle in state of Washington, in San Francisco, in Sunnyvale, and in Waterloo in Canada. We have raised over $100 million in investment from various investors who are passionate about climate change and sustainability. This technology that I'm going to talk about is a 190-year-old technology called switch reluctance machines. And my presentation is divided into 4 sections. I'll go through the history and background of SRM, switch reluctance machines. I'll give a little bit of an introduction and overview of technology application and the impact that we have. I'll also touch upon that how we are using cutting edge simulation running on powerful tools to allow us to develop products faster and innovate faster. And last, most important part of this presentation is that I would like to make a humble, ambitious wish for SRM to be in electrical vehicles, EV or e-mobility space. The key messages from my presentation are that SRM is a very fascinating technology. It has many strong benefits. It also has some disadvantages, and a lot of progress is made towards solving and commercializing this technology. We have proven our value proposition about energy efficiency in air moving applications like fans and blowers. And the technology is not there yet, but our goal and desire for it to go into EV and e-mobility. So with that, I'll start with my presentation. As I said that I'll go through history and background, introduce our technology, touch upon some simulation-driven innovation, and make a case for SRMs in electric vehicles. So as I said that SRM is a very old technology. Before I go into the presentation, I would like to use a familiar expression that Isaac Newton said in 1675, that if I have seen further, it's by standing on the shoulders of giants. So here I'm giving credits to the pioneering work done 200, 300 years ago by some passionate scientists whose benefits we are reaping today. Um, so Andrew Murray Ampere, who found the law of intensity of magnetic field, which is proportional to the current that produces the magnetic field. Michael Faraday and Lenz, who gave us the law of electromagnetic induction. In words, it is like induced voltage in a coil is equal to the time rate of change of magnetic flux that links the coil. And Lenz gave us the direction of the magnetic induction. Lorentz gave us an explanation about Lorentz force experienced by a current carrying conductor when it is exposed in a magnetic field. And this force is proportional to the magnetic field intensity, the current, and the length of magnetic field. All electric machines that we are using today, they work directly based on the work of these great scientists. And maybe there are some more. The field of electric motors has been an evolution rather than a revolution. Many people got similar ideas separately from each other in lots of different parts of the world. Here are some of the really seminal milestones that in 1800 in Italy, Volta Piles was developed by Alejandro Volta, which is like the equivalent of modern day batteries. In 1820, a Danish scientist, Hans Ørsted, saw that when he was moving a current carrying devices around a magnetic compass, the needle was, he saw a movement of needle, and that was the basis of electromagnetic field generated by electricity. In 1821, Michael Faraday devised an experiment to demonstrate this electromagnetic field. In 1822, Peter Barlow made an invention of a spinning wheel using the law of electromagnetic induction, showing a continuous motion. And in 1825, William Sturgeon invented electromagnet with a practical purpose. Until then, most of the electromagnetic work was for toy kind of things, not for doing real practical work. In 1825, William Sturgeon demonstrated that you by winding a lot many number of turns on a soft magnetic material, you can actually enhance the magnetic field to do some practical work with it. So it's the foundation of electric motors and electromagnetism in electric motor that we see today. The reluctance motors were amongst the earliest motors to be developed in 1830s and 1850s, and mostly it is to convert like a once only attraction of an oscillatory movement into a continuous movement, useful movement that you can use for doing something. These were strongly influenced by steam engine, and they were called electromagnetic engines because of the similarity and the mindset behind developing these electromagnets to do work that was done by steam engine. So earlier motors have a very strong resemblance with steam engine. Electromagnets are thought as cylinders. Poles were considered like pistons, and the switching devices or switching arrangements that were used to turn the current on and off going through different coil windings were thought of like valve gears. So it's a very fascinating journey from 1830 all the way to 1860. Everything changed in 1883 when Nikola Tesla showed a practical AC induction motor. And the rest is, as they call it, history. That motor has served a great purpose. It's a very scalable, highly reliable, and has fueled the modern world that we see today and took us this far in terms of industrial advancement. So a lot of prosperity and advancement that we see today, really the credit goes to those passionate scientists and scholars who worked tirelessly 200 some years ago. Anyone who is really interested into this fascinating history of electric machines and electromagnetism, I really like these two books and these two websites, and they have nice pictures, chronological advancements about the history of electromagnetism and electric motors. So that's in a nutshell kind of a history of electric motors going back to 1830, where the first switch reluctance motors were conceived for lifting weight and doing oscillatory and continuous motion. Today, electric motors come in all shapes and sizes. Predominantly, there are 4 types of electric motors. A brush DC motor is one, and uh, it is called DC machine. It is part of DC machine. It has several different types of DC machines, some with permanent magnets and some without permanent magnets, but they are the early motors before the switching devices were easily available, like MOSFETs and IGBTs. On the AC side, we have 3 dominant motor technologies: induction motors, permanent magnet motors, and reluctance motor. Within reluctance motor, there are switch reluctance and synchronous reluctance. And at Turntide, we are predominantly focused on switch reluctance motor because that is proving out to be the best value at a price performance and ruggedness point of view. So what is a fundamental difference between, say, an induction motor and a switch reluctance motor, or a permanent magnet motor and a switch reluctance motor? So as I said, that brush DC motor, induction motor, permanent magnet motor, they all work on the basis of Lorentz force, which says that whenever you have a current carrying conductor exposed in a magnetic field, it will experience a force called Lorentz force. And that's the fundamental physics behind the motion or force or torque in an induction motor, in a permanent magnet motor, in a brush DC motor. So what you need for Lorentz force to work is you need a magnetic field, and you need a current carrying conductor exposed in that magnetic field. And that's where you need 2 sources. One is for establishing the magnetic field, and other one is to carrying the current. In induction motor, you have windings on the stator and windings on the rotor, and that's how you, through induction, you get 2 separate magnetic fields and a current carrying conductor. And as an interaction, it generates the torque. In permanent magnet motor, we do not need the induction because permanent magnet creates that magnetic field that we need for generating Lorentz force. So either way, either through some sort of a winding or through permanent magnet, you need 2 sources for generating this Lorentz force. On the other hand, reluctance force is proportional to the current or flux density in an air gap. You do not need a magnetic induction and a secondary magnetic field. The force is generated directly as a result of an electromagnet attracting a magnetic material like an iron, a piece of iron. So it's a direct energy conversion, and that's the biggest difference between a permanent magnet motor and a reluctance motor, that the dominant torque is generated by reluctance force in a switch reluctance motor in an SRM. Switch reluctance motor is a very simple motor. There are no windings on the rotor. There are no magnets on the rotor. Rotor is just a piece of iron made from a silicon steel material, stamped from silicon steel material. On the stator, there are concentrated winding. So it's a very simple mechanical construction. There are no magnets or windings on the rotor, and that has some great advantages in terms of ruggedness, in terms of reliability, in terms of keeping the rotor cool and getting the heat dissipation out from the rotor, which is a challenge in induction motors and maybe even in some permanent magnet motors too. So it's very easy to make and very reliable and very rugged. So for about 190 years, even though switch reluctance motors have been in existence, they have gone through up and down of their fair share of being used for uh, actual industrial application. And that love-hate relationship is based on uh, some of the strong benefits that this technology has, but some disadvantages or some cons that it has. So here, everything in green is like an advantage, and in red is a disadvantage. It's a single source of excitation, so there are no magnets or windings needed on the rotor. You only have windings on the stator, and that's enough. We will see later that it has a fantastic a constant power operation, which has nice appeal to many applications, including traction for traction and propulsion application. No other motor has so much of constant power operation capabilities than SRM. For example, in permanent magnet motors, you have to do field weakening, and you only can do so much due to safety and demagnetization concerns. The construction is very simple. Just the rotor and stator, they come out from the laminations, and you put the winding, and you're ready to go. It's highly rugged and reliable, high temperature capabilities, high speed. It has a very robust insulation because rotor is pretty cool. So there is no significant heat losses in the rotor. That means that rotor does not need a lot of cooling, means that the path to cool the rotor is through bearing. So you have an improved bearing life. And several other advantages like safe against shoot through and high voltage fault. On the other hand, maturity of technology is a problem. Switch reluctance motors were not known to have high peak efficiency and power density. The physics of the motor is such that the noise and vibration is a byproduct of the useful torque. So that is a great disadvantage. And torque ripple has been another one. It's a highly nonlinear machine, which means that even small changes may result into big differences into the performance. That makes it harder to design and harder to control. Up until now, it was a problem that it doesn't run without power electronics, but now most motor drives are running with power electronics, so no longer it's a problem, and it needs precise position feedback for control. So the commercial reality has been that it saw a first wave in 1830 to 1850, looked promising. Everything changed when induction motor became popular. Second wave of SRM came in 1960s when MOSFETs and power transistors were easily available. In 1980, a professor from University of Leeds, Professor Lawrenson, founded a company called SR Drives, and they developed numerous applications for SRMs, and that company got bought over by NIDAC. Since then, SRMs have been used for many high reliability applications. For example, a cooling pump in a cooling tower of a nuclear reactor. Here on the right-hand side, I show a picture of a 2 megawatt SRM for ship propulsion application. But largely, SRMs remained a technology of the future that didn't arrive because of some of the issues that I mentioned. I think it's hard to see here. but 2014 DOE published a report comparing induction permanent magnet and SR technology. Even though SR technology got the highest points compared to induction and permanent magnet motors, um, because of those disadvantages, maturity of technology and difficulty in designing and torque ripple and efficiency, those problems, SRMs didn't become mainstream. And that is what my research in 2002, when I started my graduate studies, that was one of my goals, to address some of those limitations, because this is a fascinating technology, very cheap, highly reliable, very rugged. If we are able to solve some of these problems, it has great promise. So that is what I started doing in 2002 at Illinois Institute of Technology. And since then, um, it has been a fascinating journey for me. I invented this concept of high rotor pole switch reluctance motor, and went through my PhD through it, applied for a patent, got a patent. And in 2014, I joined with a couple other people to co-found Turntide to commercialize this technology, because as a result of something very simple, by putting in more number of rotor poles, it did some fascinating things. It improved the efficiency to a point where we are comparable to permanent magnet motors in some testing that we have done. So it gives you higher efficiency, higher torque, higher power, because motors are thermally limited. If it is more efficient, means you have less heat dissipation and you can push the power more. Uh, so we have won numerous awards at Turntide. We have won Clean Tech Open Award in 2012. We have won NSF National Science Foundation SBIR grants. And currently we are in production. Here I'm showing a picture of our warehouse. So it's not a lab setup. We have thousands of motors operational and running, and it is in production up to 25 horsepower. We also have some custom motors for direct drive application, for low speed, high torque type of applications. So basically, in a nutshell, that why high rotor pole, why putting in more number of poles in rotor improves the torque and efficiency. There are two explanations. One is, if you look at the torque equation, average torque is directly proportional to the change in co-energy, number of phases, and number of rotor poles. By increasing the number of rotor poles, you are able to increase the torque. Also, another artifact of increasing the number of rotor poles is that you get more area for the copper, more winding, that allows you to reduce the copper losses. And as a result, we get higher efficiency, higher torque, low torque ripple, and reduced noise and vibrations. So very quickly, I'll go through our product range. On the hardware side, we have an ultra efficient motor. We have a motor controller called drive or an inverter that is needed to run this motor, and something called supervisor, which is like a gateway for an IoT connectivity. On the software side, we have a cloud IoT software for configuring and programming the system. Also a very rich data analytics and monitoring and reporting functionality. So our main components, these are our four main components: motor controller, motor, supervisor, and a cloud-based capability. All these are designed by us to work seamlessly as a system. And the result is that we have a highest efficiency, smartest motor, and the most reliable system. I'll quickly go through some of the slides just to highlight the product that we have. So our motor has very proven reliability and efficiency. It comes in standard frame sizes because our focus is energy efficiency into air moving applications to begin with from a business point of view. We have a cloud enabled motor controller that controls the motor torque and speed. And the supervisor allows us the connectivity through a cloud service and data reporting and data storage and analysis. So our architecture is that each motor has its own controller, and those controller can directly talk to the cloud or via supervisor. And that gives a lot of options and powerful monitoring and control and analytics capabilities. So our current product range for heating, ventilation, and air conditioning, we have up to 25 horsepower. Again, one of the characteristic of switch reluctance motor is noise. And we have a quiet switch reluctance motor and some custom application for direct drive type of applications. Motors are everywhere, and they're actually a hidden driver of our climate crisis because they use 47% of the electricity, and a bulk of it is wasted because you may think that, well, aren't motors 95% efficient? Well, only at rated operating point, and only some motors, not always. So our motor, switch reluctance motor technology, has from at rated, we are 7% more efficient, and at other places, when you are not running at rated torque and speed, we are up to 15 to 20% more efficient. So this is a comparison with a NEMA, standard NEMA premium efficiency motor in red versus a Turntide switch reluctance motor, again for a commercial industrial type of application. We get similar results for 3 horsepower. When we apply a fan affinity law where the power is proportional to the cube of the speed, the energy savings are just astronomical because most of the heating, ventilation, air conditioning systems, they run at a very lower speeds and lower torque. So you get up to 30–40% energy savings. Several studies have performed independent third-party NREL, Energy Trust, and they have found from 11 to 71% energy savings. So those are really some big numbers. And think about for a moment that if we can bring these somehow into other applications like electric vehicles, there is a real implication in terms of range and affordability and the cost of ownership. I'm going to skip through some slides because I do want to get to the EV part, which is very exciting for this audience here. So here, I'll skip through the simulation-driven innovation. One of the biggest challenge with SRM is that it has a very high linear, highly nonlinear physics, has strong dependencies on control, and it's very hard to optimize because it has just so many parameters that needs optimization. So at Turntide, that has been our biggest, one of the biggest breakthroughs, that we have used very sophisticated tools running on powerful computers and run thousands of simulations in virtual environment to be able to optimize and faster optimization for better performance for a real product, going from a concept to a real product in a less than 6 months. So in last portion of my presentation, I would like to make a case for electric vehicles and SRM and why there is a fit for an SRM, because there are some very interesting things happening. Again, every motor has a place, and we hope that SRMs get there in electric vehicle space and e-mobility space. But as you can see, I mean, there is a broader trend for more electric vehicles. This is a fascinating slide that if you look at market capitalization per car sold, Tesla is at 1.4 million per car, and there's quite a bit of an excitement towards electrification of anything that moves, whether it is people or goods or material. there is a motor is a key component for EVs, for drivetrain, and for many other pumps and compressors and other usage, which is mostly dominated by rare earth-based material. So there is a worldwide motivation for developing rare earth-free motor technology. And there are three main avenues: using copper-based copper rotor for induction motors, or find rare earth alternatives, or reluctance technology, synchronous or switch reluctance. Reluctance motors are already used in many vehicular applications, like a wound rotor motor with continuous slip rings in Renault. And they have no concerns for reliability or life because it's a continuous slip ring. There is a company in UK, Advanced Electric Machine. They are working on SRM for commercial vehicles and passenger cars. Superchargers, starter generator, exhaust-driven generators are also an application for SRMs. And off-road construction and mining equipments, Komatsu, John Deere, Caterpillar, they are using reluctance motor. So what gives me hope that SRMs will grow in vehicle applications? Because of these four reasons. SRM advantages are too compelling to ignore. This technology is improving more rapidly than other technologies. In lab, we have seen that SRMs can exceed a permanent magnet type of performance in vehicle application, and there are issues with rare earth metals. So some of those advantages are the extended constant power range, which is optimal for traction application. There are no magnets, no winding on the rotor, so it gives lower inertia and cooler rotor, longer life. Also, SR motors are efficient where it matters the most. They're one of the highest reliable, rugged, and long life technology, and it is rare earth free. So what I mean by an extended constant power range and why it is good for a traction application, what you find through gear mechanism, that's what extended constant power operation gives us. It is very rugged. SRM is very rugged because there are no distributed winding, and concentrated winding has some nice advantages. We have made tremendous improvement. In last 10 years, we have improved the efficiency to be near to a permanent magnet motor. The noise has been reduced drastically by about minus 20 dB. That convinces us that there is a potential for SRM. Professor Chiba in Tokyo Institute of Technology in Japan, he designed an SRM and compared it with a Toyota Prius third generation IPM motor. And for 6% more weight, about 3 kg, everywhere else that SRM has a better performance. Here is a performance comparison between that IPM, Prius IPM, and a switch reluctance motor. And where you see everywhere that is blue, it is when IPM is more advantageous, and everywhere else, SRM has a higher efficiency. So except for that low speed, high torque area, everywhere else, SRM is more efficient. Fourth issue that faces permanent magnet motors is the rare earth dependency on rare earth elements. And just today, I saw these two news that that again heighten the sensitivity towards supply chain and predictability and volatility. There is also an element of environmental cost for rare earth mining of rare earth metals. So putting this all together, future is very exciting for electric motors, more for SRM than for others, but all motors will benefit from all these exciting new trends, amorphous nanocrystalline based material, which has very superior magnetic properties. There is a lot of research going on in 3D printed or injection moldable steel infused with nanocarbon based material to improve the magnetic properties. copper diffused with nanotubes can behave like a superconductor at room temperature. So that's an exciting area for pushing this performance even further. There are tremendous research happening where the magnetic structure becomes suspended bearing. So you can go with higher speed without those extra losses from the bearings. Next generation cooling technologies and a lot more. With that, I would like to stop here. I know I kind of went through a marathon marathon presentation. I realized that I had more slides than I was able to cover. So I apologize for skipping some of the slides, but I'm more than happy to answer your questions. Thank you so very much for listening to my presentation.
Thank you, Dr. Desai. We're going to go ahead. We have some questions coming in. So I'm going to ask one of you for Mr. Walton Fair. Could this technology be useful in Vtol or hybrid VTOL aerial vehicles?
So I cannot discuss much, but we are just in a discussion with an OEM, which are into space vehicles. And that's where pushing, they would like to use it for short-term duty ratio, only for 11 minutes. And they would like to push the envelope much further. And reluctance motor technology, you can push it much further because of some of the advantages I discussed. So I'm hopeful that there is definitely a potential for some of those very demanding, aggressive applications.
Okay, thank you very much. We have another question in from Thomas Sutrina. Thomas, I'm gonna, if you're okay with it, I'm gonna allow you to go ahead and ask that one live.
Actually, he answered the question.
Oh, okay.
Right after I sent it.
Okay, well, thank you for that. I think the one that I think would be interesting to a lot of folks on here that you asked, I'll just let them maybe reiterate it. Tesla has chosen a hybrid motor replacing an induction motor. It is both reluctance and PM. Do you know why they made this choice?
So there is a little bit of technicality in there. That a difference between a reluctance motor and a permanent magnet motor depends on how much of the torque is produced by reluctance torque versus the Lorentz force, and how much is the magnetic material. So I think there is a push for reducing the magnetic material for cost and reliability reasons. Again, more magnets you have, you get more efficiency in higher torque region, but the same magnet hurts you when you are running faster in lower torque region in fourth gear, because you have to now overcome the magnet. Actually, you are fighting magnet. You are opposing a magnet. You are wasting current to actually cancel the magnetic flux produced by your permanent magnet. So reducing permanent magnet content without sacrificing the performance much is really a very useful thing. And that's the direction from a cost, reliability, and performance point of view that I see, and that Tesla has that similar flavor in saying that we have a reluctance motor and less of a permanent magnet and more of a reluctance.
Okay, thank you, Dr. Desai. Next question from Sage Han. Has this control scheme been implemented on an embedded platform? Does the motor scale to smaller applications?
So the smallest we have gone is up to like 1/4 horsepower. And in nothing in the technology and nothing in our experience says that there are fundamental physics-based limitation of not scaling it down. Obviously, from a business point of view, many of those low power applications have been either induction motors or brushed DC motors because there is no power electronics associated with it, or the power electronics is much simpler versus in a switch reluctance motor, you will require a full-blown drive. we do have some applications that we have explored, are exploring, for example, in power tools, um, which are very low power, fractional horsepower type of applications. So currently, I'm not aware of that there is any ASIC that is developed to have a dedicated control, IC-based control for a switch reluctance motor, but there are lots of low-cost processors that can be used to control a switch reluctance motor in a cost-sensitive, low-power applications.
Okay. Our next question comes from Michael Sullivan. Could you explain in more detail the difference between switch reluctance and synchronous reluctance?
That's a very good question. So they both are from reluctance family, meaning they don't have windings on the rotor, no magnets on the rotor. The difference is mostly in construction and the electromagnetic field distribution. So for example, in synchronous reluctance motor, you are using a distributed winding and there is a sinusoidally varying magnetic field that is sweeping across the rotor at the synchronous speed. There is no saliency, means stator and rotor are pretty much round. You try to make them perfect circle in synchronous reluctance machine. Versus in switch reluctance machine, you have a saliency, you have a stator and rotor, they have a distinct shape to generate change in inductance and maximize the change in inductance, minimize the reluctance and maximize the ratio from unaligned inductance to aligned inductance. So those are fundamental differences in terms of principles of constructions and how it is manufactured.
Okay, thank you. I'm going to now let Luis Diaz ask a question live. Luis?
Hi. Could you just explain a little bit more about the root source of the vibration? What's really generating the extra vibration in this type of motor?
Yeah, that's an interesting question, and I would say millions of man hours have gone into researching that that phenomena and trying to address it. And we have some patented technology where we are able to reduce noise by about 15 to 20 dB. But the source of force in a reluctance motor is an attraction between an electromagnet and a piece of iron. As the rotor moves, which is a piece of iron, as the rotor moves, that's an attraction. Instead of torque, we get an attraction. Torque is produced by tangential force, and vibration is produced by radial force. And as the rotor aligns itself with the stator or an electromagnet, the radial force increases more drastically than the proportional increase in the tangential force, and that causes the due to switching, it is literally doing this at a microscopic level. So your stator is like a drum, a rotating drum, which is becoming like an oval as it rotates, as the switching of one phase to another phase to another phase to keep the switching keeps moving from one phase to another. So basically the physics of the motor is responsible for creating radial forces, which is creating these vibrations manifested as an acoustic noise.
Okay, great. All right, now I'm going to let one of our student members, Antonio Salerno. Antonio is a student at University of Illinois, Chicago. Antonio, go ahead and ask your question.
Hi, I was wondering if it is possible to get regenerative braking with a switch reluctance motor.
Yes, yes, SRMs can be used as a generator. One caveat is that because there is not a source of magnets, or there is not a, so when you start the motor, first time, there is no magnetism because there is no permanent magnet. So first you have to establish a magnetic field. So you have to spend, so it's like starting your furnace. You have to have a pilot, and then it becomes a self-sustained fire. So in case of a switch reluctance technology, you need to spend some energy in the beginning to start that fire, to diffuse the magnetic field, to establish the magnetic field, and then you switch it over as a generator, and it works perfectly as a generator, not a problem.
Okay. Another question here, Dr. Desai. Tell us a little bit about the startup process for starting your company and maybe some of the biggest challenges you faced.
That's a very very interesting question. I think so. For example, switch reluctance motor has these 4 or 5 problems: maturity of technology, efficiency, torque ripple, vibration, and peak power density. The difference in terms of a startup is that we focused on the business case of solving the problem. There are many problems with SRMs. There were many problems with SRMs, which are meaningful to solve, that allows us to have a commercial application, that allows us to demonstrate, get our feet in the door, demonstrate the value proposition. Because if we have a perfect motor, all the applications are open for us. And if we have a very sucky motor, then no applications are open for us. So which one do we go after so that a door opens for us that allows us to continue developing the technology, continue with the business case, continue with the fundraising, proving out the concept, proving out the value proposition, so that the more funding can be attracted and more development can happen. And that's, I think, the biggest learning, biggest lesson that I, as a PhD, from a technical point of view versus a business point, try to solve the problem in the context of a business problem.
Okay, thank you. Okay, we have another question that just came in. What simulation tools do you use in your design process? This is from Michal Spazov.
Yeah, we are using Maxwell from ANSYS. So we have a suite of ANSYS tools. We use ANSYS Maxwell. We use ANSYS Mechanical, and ANSYS Mechanical has structural and thermal and harmonic and acoustic and all those other subset of tools. But we use finite element analysis for electromagnetic design. That is very important because SRM is highly nonlinear, and is like with any the characteristic of a nonlinear system is that we all have heard about the butterfly effect, that if you clap in Chicago, there could be a hurricane in Florida based on the nonlinear system. Nonlinear systems, you make very small change and it can have a unimaginable big impact. And we see that in SRM design. That's our specialty, how we design switch reluctance motor using finite element analysis in a way that we can maximize the performance, and our predictions are highly accurate to a point where prototypes are just meant for a confirmation of what we were predicting. We were not checking them for performance. We are just validating, yep, this is what we think it will do, and that's what it is doing.
Okay, thank you. Well, we're right up against time here. We do appreciate it, Dr. Desai. Tim, I'm going to turn it back over to you for any parting words.
Thank you, Dr. Desai. It was an informative presentation. Sorry that it had to be compressed. It looked like there were some other interesting slides there, but we appreciate you taking the time to be with us tonight and present your obvious significant knowledge in this arena. So thank you again.
Great pleasure.
I also want to thank Alvin Chin for helping us get the word out with IEEE VTS. And just a quick reminder that for SAE, Chicago, we have an event coming up on Tuesday, February 2nd with Caterpillar, that was mentioned earlier, with their autonomous mining programs. You could check out our website for an announcement there. We'll be publishing a flyer here probably tomorrow. So we got a late start on getting this one going, but it should be a very interesting event with Caterpillar. So reach out if